Hello AP Chemistry and welcome to electron configurations, which again should be kind of a review because we did this last year. We'll just do a little bit more and a little bit differently and a little more thoughtfully. So anyway, electron configurations. This is the arrangement of electrons in an atom, okay? We learned these last year, right? Aufbau principle states, ding, 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 we always fill lowest energy up. So we're always going to start at the lowest energy orbital available and work our way up from there, okay? And this is where the diagonal rule came into play last year. But hopefully you remember this well enough that you don't really need that because it's all literally written on the periodic table for you. Like the periodic table is the most beautiful, like, board game, kind of, right? Where everything is already laid out in its proper place. You just need to interpret where it sits, okay? Hund's rule, right, applies to degenerate orbitals, where what does degenerate mean again? Right, equal energy. So when we have orbitals of equal energy, for example, a set of p or a set of d or a set of f orbitals, we will divvy the electrons one into each first and then we pair them after, okay? So applying these things, here are some electron configurations already written out for you, right? Lithium, right, which has 3 electrons. By the way, where do I find this number? Right, for a neutral atom, that is our atomic number, okay? So for lithium, if we have 3 electrons, we're going to start in 1s, and again, we have the opposites pointing arrows to signify the m sub s values, right, the magnetic spin numbers, and that they spin in opposite directions, okay? And then we put 1 into the 2s, right? If we have 4 electrons, we put 1 in each, right? If we get to 5, then we put here carbon. Here's where we start to apply Hund's rule, okay? And we've spread them all out before we start to pair them, right? And then when we get to neon, right, they're all going to be full. And then we go on to the next one, which would be our 3s, okay? Now, this is our orbital notation, wherein we sort of write out our shell, subshell, and we depict our orbital and our electrons. So it's kind of like we can see all 4 quantum numbers when we're looking at an orbital diagram. Electron configuration would be the shorthand version, where we're going to give our orbital, we're going to give our shell, our subshell, and how many total electrons are in that subshell. Okay, which is why when we get down here, for example, to our p's, right, we're just going to say how many total electrons are in those p orbitals, and it's your responsibility to understand how they're distributed. Okay, now we also have another shorthand known as noble gas notation. Now, noble gas notation starts with a noble gas, where we use a noble gas to represent our core, and then we just depict the valence, right? Valence meaning, right, the outermost electrons, okay? So if we look here, this would be valence, 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 okay? Valence being your highest shell, yes, your highest shell. Okay, now that means everything that's in your core can be symbolized by whatever noble gas it represents. Okay, not written up here is helium, which has 2, which would just look like 1s2. So we'll note that all of these that have 1s2 only, their core would say He, and then we would say 2s1. So this one would be He, 2s2, He, 2s2, 2p1. Okay, so for the second period, He is not a huge shortcut. These square brackets take as long as writing 1s2. When we get down here, though, 1s2, 2s2, 2p6 represents neon. Yes? So here my core is now neon, and it starts to be a significant shortcut. Yes? Whereas in these 10 are represented by the electron configuration of neon, and this is how we shortcut that. Okay? And that's referred to as noble gas notation. All right, moving along, what the table really looks like. So when we think about our periodic table, right, these are actually located underneath because this is obnoxious to look at, right? But we understand that these are our S blocks, so this is groups 1 and groups 2, okay? This is our S block, wherein the period corresponds to which shell we're talking about. And when we're filling elements here, right, these are going to be our S electrons, right? Over here are our p electrons, where again our period corresponds to our shell. Okay, and note that there are 1, 2, 3, 4, 5, 6. Oh, because there are 6 total electrons that fit into our set of p orbitals. D's are always back a number, right? So here's our 4, 4s, 4p. D's are back 1, right? But there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which happen to fit the fact that we have 5 orbitals, each can hold 2 electrons for a total of 10, right? And here we get the same thing where this is 14, and note that that's back 2, okay? All right, let's do some practice. Let's say that we wanted to write the electron configuration for bromine, okay? So first of all, we'd have to go find how many electrons it is, which is 35. If you can't read this table, obviously you can go look at your own. But if we wanted to do bromine for 35, we could write it all out as in 1s2, 2s2. And by the way, let's talk about how we do that, right? Let's get a different color. All right. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember, here starts our D's, right? So this is 3d10. Then here goes 4p1, 4p2, right? 3, 4, 5. Yes? So we would know that this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, and 5. Okay. Now, this means there's never a reason to get one of these wrong because it's written out over here. Okay. Now, if we wanted to do noble gas notation, right, then you might say, oh, well, I still have to count all this out. No. If this is bromine, we go find the noble gas before it, which is argon, and then we just write what comes after it, right? So 4s2, 3d10, 4p6. Okay. If you prefer, you can put the 3's in front if you prefer that, but this is fine. So then if we wanted to do barium, for example, let's say we wanted to do barium. We go find barium. Barium has 56 electrons. And let's say we just wanted to do noble gas notation. So if this is barium, the next nearest noble gas would be xenon. So after xenon, we have 6 S1, S2. Yes? All right. Let's say we wanted to do, I don't know. Let's say we wanted to finish up with polonium, okay? We would have our, well, that's in the same period, right? So we have our 6s2. Then don't forget that here is my F, right? Which is back 2, so this would be 4f14. And then we would do my back 1, so 5d10. And then we would pick up with my 6, 1, 2, 3, 4. And that would be the noble gas notation for, well, now we're talking about polonium, okay? So what that kind of means is that when you look at a periodic table, this is what you should see in your head, okay? Wherein the location like spells out our electron configurations, right? Which is super convenient and super necessary that you can look at a periodic table and pick up on all of this. Because in the next chapter, we're going to start talking about trends, right? The fact that all of these only have one valence electron is a trend, and that sort of dictates their behavior, right? The fact that they're all different, though, by one shell also helps to dictate their behavior, right? Likewise, as we go across a period, as we're adding electrons to the same shell, that's a trend that you're going to be able to explain in terms of like the kind of behavior that it causes, right? But all of that is so much easier if we can see all these configurations. So really important that you can see all this, and if not, you need to be spending time with me until you can see all of this. All right, thanks for listening, be good, and I'll see you soon. Bye.